Hi everyone. In this video we're going to begin to talk about an inverse function. Okay? And inverse functions play an important role in the rest of the topics that we cover in this course and in all of mathematics. And so this is an extremely important section for us. And so first we need to define what an inverse function is. So I included it here from the book. It's quite a long definition. Okay? Suppose that f is a one-to-one function, which we learned about last time. Then, corresponding to each x in the domain of f, there is exactly one y in the range. Okay? And corresponding to each y in the range of f, there's exactly one x in the domain. Okay? The first is true because f is a function. The second is true because f is one-to-one. Okay? In this sort of definition, mathematical definition type stuff, they need to lay out the facts first. And so that's what they're doing in the first two sentences. Okay? The corresponding range of f back to the domain of f is called the inverse function. Okay? The symbol f inverse, or f raised to the negative 1 power, is used to denote the inverse function of f. Okay? And so what they mean is that if I have in a graphical representation sort of what we were doing before of a domain and a range, okay, we have different numbers in the domain like 1, 2, 3, 4, and 5, and then they're related to members of the range, okay, or they're mapped, or there's any number of names that we use to denote this, but they're mapped to certain numbers in the range. And they're mapped using some type of function. And I'll call that function f. And so maybe my mapping function is 4x. Okay? So 4x. And so 1 would be mapped to 4, 2 would be mapped to 8, 3 would be mapped to 12, 4 would be mapped to 16, and then 5 would be mapped to 20. Okay, so hopefully that makes sense. I just evaluated the domain number to get the range, but that is what the domain and the range are. Okay? And so we talked about the domain and the range of a function. Okay? And this is just a graphical representation of it. So that gets us from the domain to the range. But what I'm interested in here is another function that gets us from the range back to the domain. So I want to go the other way. And the function that does that is called f inverse. Okay, and so we have an example here. I have a one-to-one function, and it's unlike the functions that we've been working with a lot lately, but we have worked with this xy pair representation of a function before, earlier on in the course. And the simplest way to describe finding the inverse function is you switch the x's and the y's. Switch the x's and the y's. And so what that means is that for these points in this xy pair group here, is you switch the x and y's inside their respective points. So the inverse function, f inverse, my pen isn't isn't cooperating with me right now. So F inverse is, again, the set of points, but that first point is -27, -3. So you see all I did was switch the x's and y's in the points. Okay. The next one would be -8, -2, -1, -1, 0, 0, and then 1, 1. Okay, so that, of course, those didn't change because the x and the y's were the same. Okay, but then 8, 2, and 27, 3. Okay, and so that is the inverse function. So all I did for those xy pairs was switch them. And that idea is going to persist throughout finding these inverse functions. Okay, so that's the inverse of a function. And so here's a prettier picture of what I drew before. F is going to get us from the domain to the range. F inverse is going to get us from the range back to the domain. And so you see there's a relationship between the domain and range of F and the domain and range of F inverse. Namely, that the domain of F is equal to the range of F inverse, okay, and then the range of F is equal to the domain of F inverse. So that will come into play later on. Okay. Two important facts that we need to keep in mind here and we'll use later on is sort of the consequence of an inverse function. If I can find an inverse function, if it exists, then if I do these operations down here, if I take the inverse function of the regular function, F inverse of F of x, the number I get out is x. Okay, so if I take F inverse of F, that's x. Notice that this is a composite function, which we worked on in the last, not specifically that, but this together is a composite function. Okay, and so F inverse of F has to equal x, where x is in the domain of F. Okay, and then similarly we have another composite function here. F of F inverse also equals x. Okay, and so they cancel each other out, so to speak. Okay, so F inverse and F cancel each other out. All I'm left over with is x. In the same way, F and F inverse, if you switch them, they also cancel each other out. I'm just left with x. So we can use that fact to verify if two functions are inverses of each other. Okay, so I have a function g, and then the inverse function I'm claiming is the cube root. So g is x cubed. I'm claiming that the inverse is the cubed root of x. So in order to verify that g to the -1 power of x really is the inverse, I just need to evaluate g of g inverse of x. Is it really equal to the value x? So composite functions, I put the entire value of g inverse in for any x that I see in g. And so I see 1 right there. So I get the cubed root of x cubed. That's the composite function. Okay, and the cube and the cube root cancel each other out, and so I do indeed get that g of g inverse is equal to x. Okay? And then I'm going to do the same thing with g inverse on the outside. G inverse of g of x. Okay, what does that equal? I place the entirety of g into wherever I see an x in g inverse. And so that's the cubed root of x cubed. Okay, so that's the composite function. Again, the cubed root and the cube cancel each other out, and I do indeed get x for that. So they are inverses because both of those composite function calculations work out. Okay, and so we can do the same thing with this second example. Down here, 2x plus 3 and 1/2 x minus 3. So we first need to look for f of f inverse. I plug the entirety of f inverse into any x that I see in f. So I get 2 times 1/2 x minus 3 plus 3. Okay, and I made sure to put parentheses around everything so that we wouldn't get confused. But when I multiply 2 on the inside, okay, 2 times 1/2 is 1, and so they cancel out. I'm left with x minus 3 plus 3, which the minus 3 and the plus 3 cancel out. And I get x, so I'm halfway there. And then I have to do it backward, or the other way. I'm placing the entirety of f in for anywhere that I see an x in f inverse. So that's 1/2 quantity 2x plus 3 minus 3. 1/2 times the quantity 2x plus 3 minus 3. The plus 3 and minus 3 cancel out, and then I simplify to 1/2 times 2x. The 2 and the 1/2 cancel, or equal 1, and so I get x. And so indeed, both of those calculations get me to x. I'm good. Okay, so that's how you verify an inverse function. You check that both of those are true. Now, an important part, or rather an interesting part, about the graph of an inverse function is that the graph of the inverse function is symmetric with the graph of f and the graph of f inverse are symmetric with respect to the line y equals x. Okay, and so here we have an example with f of x here that's in blue, okay, and then the inverse function is in red or purple, okay, and you'll see that they're symmetric about the line y equals x. We won't do a lot with graphing inverse functions, okay, but it is an important point, and so you should take note that this is true. So, now we get to the interesting part, and that's finding an inverse function where we're not just looking at points. So before, at the beginning of the video, we could just say, easy, we switch the y's and the x's, and then that's the inverse function. But now we're given an equation. Okay, now we're given an equation, and so we need to use that equation to find the inverse. And so what you do when you find an inverse function is you do basically the same thing that we did for the points, is that you switch x and y. Okay, so just like we switched the x and the y coordinates for those points, we're just going to switch the x and y placeholders for this function. Okay, and so that's what we do. That's what I say up in this first point. Okay, so what we're going to do, it's defined by switching the two. So if f is defined by y equals f of x, okay, then the inverse function is defined by the equation x equals f of y. So we're going to switch the x and the y, just like we saw before. But then what we're going to do is solve for y, because we're used to things being in terms of y equals something. So first we want to switch the x's and the y's and then solve for y. So our function is 2x plus 3, and so really we should write y equals 2x plus 3. Okay, then we're going to switch the x and y, and so we get x is equal to 2y plus 3, and then we're going to solve for y. So we subtract 3, and I get x minus 3 is equal to 2y, and then I divide by 2. And so I get 1/2 x minus 3 is equal to y. Okay, or you could rewrite that y is equal to 1/2 x minus 3. And so that is how we get an inverse function. Really not too hard. Okay, really not too hard. You just switch the x and the y and then solve for y. So here's a general procedure for how you find the inverse function, okay, and it highlights something that I missed, and I'll go back and do, is that you first interchange the variables, switch x and y, then step 2, solve the function in terms of y, and then in step 3, what you need to do is you need to check the result, okay? So this is an important step and not an optional one when you solve for an inverse function. So you should switch the x and the y's, solve for y to get your possible inverse function, and then check that it actually is an inverse of f. Now, actually we did this, so for my example, we had this pairing, 2x plus 3 and 1/2 x minus 3, in these examples here. So it was the second one here. And so I already verified that those two functions are inverses of each other. So I did that already. So already verified. Okay? But if you hadn't done that, or I hadn't done that previously, I would need for you to verify that the inverse is actually the inverse. So do those two composite function calculations. Okay? And so there are the general steps of finding an inverse of a one-to-one function. And so to end the video, I want you, and I didn't put everything here, but I want you to find the inverse of f of x, okay, where f of x is that. Okay, so I want you to find the inverse. So you need to switch the x's and the y's, solve for y, and then check. And so since this is a little weird, I'm going to do the first step for you. Okay, you're going to switch the x's and the y's. And so instead of having y equals 2x plus 1 over x minus 1, you're now going to have x is equal to 2y plus 1 over x minus 1. Oh, sorry, y minus 1. Okay, and so here you might get a little stuck, and you're like, where do I go? The first step is that you need to multiply each side by y minus 1. Okay, that gets rid of the bottom there, and you're left with x times y minus 1 equals 2y plus 1. Okay, so there's going to be a number of steps of algebra that are involved to get y alone, but in fact you can. Okay, so you can get, you can work down to something that looks like y equals stuff. where the stuff only has x's and numbers in it. Okay, so that'll be your inverse function. Then you check if this function, which I'm going to call f inverse, whatever you find, if you do the composite calculations with these two functions and you get that they both equal x, then you're good to go. If not, then you made a mistake in your algebra and you should go back and check. Okay, so that's your turn for this video, and that's the end of section 6.2.